Here is something strange. Take a triangle, a small one, cut from card, and shine a torch on it. Now look at the shadow on the wall behind it. Slowly, slide the card towards the torch and watch the shadow. It grows bigger and bigger. So here is the question. Is that shadow a different triangle? It is clearly bigger, every side is longer. But look at the corners, look closely. Every angle, exactly the same as before. Nothing bent, nothing twisted, the same shape, just scaled up. And that one idea, shapes that match perfectly, but come in different sizes, that is this whole chapter. We call them similar. So let us find out, what does that really mean? Chapter 6, Triangles. So what does similar actually mean? Let us test it properly. Here is a triangle, sitting on a square grid. Now watch, we scale the whole grid up evenly. Every square grows by the same amount, and the triangle grows with it. The sides get longer. But the angles? Look at the angles, they have not moved, not 1 degree. That is similar. Now watch something different. This time, we stretch the grid sideways, only sideways. The squares turn into rectangles. And the triangle? It has buckled, the angles have changed. This is not similar, this is just a different shape. So here is the lesson. Similar does not mean bigger, it means bigger by the same amount, in every direction. Here is where we are going. First, the rule a parallel line always obeys, inside a triangle. Second, the reverse of that rule. Third, the 3 quick tests that prove 2 triangles are similar. And finally, we go back to that shadow, and we measure something we cannot climb. Now, the first big result. Let us picture a sail, a triangular sail. Someone sews a seam, straight across it, parallel to the bottom edge. And that seam cuts the 2 slanted edges into pieces. Now watch the seam slide up and down. As it moves, those pieces change, all of them, every length shifting. Now look at the 2 ratios on the screen. On the left, the top piece over the bottom piece along the first edge. On the right, the very same thing along the second edge. Now watch the numbers as the seam slides. They change, of course they change. But look closer. They change together, they are equal, always equal, at every single position. That is the Basic Proportionality Theorem. Draw a line parallel to one side of a triangle, and it cuts the other 2 sides in the same ratio. It has another name too, the Thales Theorem, after the man who first spotted it. Right, let us use it. In triangle ABC, the line DE is parallel to BC. AD is 4 cm, DB is 6, and AE is 6 as well. The question? Find EC. Step 1, write the theorem. AD over DB equals AE over EC. Step 2, drop the numbers in. 4 over 6 equals 6 over EC. Step 3, cross multiply. 4 times EC equals 6 times 6, so 4 EC equals 36. Step 4, divide both sides by 4. And there it is, EC equals 9 centimeters. And here is the lovely part. We never measured EC, we never went near it. The parallel line just handed us the answer. Now here is the clever bit. Every good theorem has a reverse. So watch what happens when we tilt that seam off parallel. See it? The 2 ratios split apart instantly, not equal anymore. Now bring it back to parallel, and log equal again. So the reverse is true as well. If a line divides 2 sides in the same ratio, then that line has to be parallel to the third side. And that is how you prove two lines are parallel without measuring a single angle. You just check the ratios. So far, we have worked inside one triangle. Now, let us compare two. And here is the real question. How much do you actually need to know before you can be certain two triangles are similar? Watch this. The small triangle lifts, it turns, it grows, and it lands exactly on top of the big one. A perfect fit. But how little did we need to know to be sure that would happen? The answer: 3 tests. Test 1, angle, angle. Two angles match in both triangles. Then they are similar. You never need the third angle, it comes free, because every triangle's angles add up to 180. Test 2, side, side, side. All 3 pairs of sides in the same ratio. Similar. Test 3, side angle side. 2 pairs of sides in the same ratio, and the angle between them equal. Similar. 3 tests, that is all you ever need. Let us try one. Triangle ABC, AB is 4 cm, BC is 6. Triangle PQR, PQ is 6, QR is 9. And the angle at B equals the angle at Q. So, are they similar? Step 1, the first pair of sides. AB over PQ, that is 4 over 6, which simplifies to 2 over 3. Step 2, the second pair. BC over QR, 6 over 9, and that, also 2 over 3. Step 3, the two ratios match. And the angle sitting between those sides is equal in both triangles. Step 4, that is the side angle side test, exactly. So, yes. Triangle ABC is similar to triangle PQR. Now, let us watch this idea do some real work. This is a pantograph. 4 rods pinned together at the joints. Hold one point and trace a small drawing. Now, watch the second point. It draws the same picture, enlarged, at the exact same moment. How? Because every position of those rods forms a pair of similar triangles. The shape is guaranteed, the scale fixed by the pins. Artists used this, engineers used this, for centuries, to copy and enlarge drawings, long before any machine could. Similar triangles, turned into a tool you can hold in your hand. Now, back to where we began. A tower, right in front of you, and you cannot climb it. What do you have? A meter stick, and a sunny day, that is all. So here is what you do. Stand the stick upright, and measure its shadow. Say the stick is 1 meter tall, and its shadow, 1.5 meters long. Now, measure the tower's shadow, say, 24 meters. And here is the key. The sun's rays hit both at the same angle, and both stand upright. So the two triangles are similar by angle. Step 1, write the ratio. Tower height over stick height equals tower shadow over stick shadow. Step 2, drop the numbers in. Height over 1 equals 24 over 1.5. Step 3, divide. 24 divided by 1.5 is 16. So the tower? 16 meters tall. And you measured it with a stick and a shadow. 2 things, hold on to these. First, similar means equal angles and proportional sides, both, every single time. Second, the moment you see a line drawn parallel to one side of a triangle, reach straight for the Basic Proportionality Theorem. Almost always, it is the fastest way through the question. And that is Chapter 6, Triangles. Practice the sliding seam questions until that ratio jumps straight out at you. Notes, quizzes, and free study resources are waiting at schoolrevise.com. If this made Similarity click, give it a like and subscribe for the next chapter. Revise. Practice. Excel.